Thanks. Safe flight. Okay, so ladies and gentlemen, we're now going to put in place the parameter variation experiment depending on this. So, okay, so great. Okay, so we are going to now do something we've never done before in this boot camp, which is relax. Okay. So we are going to put in place a parameter variation experiment, okay? So we are going to take this model here, and we're going to do new experiment, and this is going to be a parameter variation experiment. I think everyone should have the version that supports that. Do you see that?
Yeah, it's just from complete
new experiment, and this will be
only have the first three.
Yeah, so I want a parameter variation.
Yeah.
Right. Okay. Parameter variation, and this will be called parameter variation parameter variation baseline. Okay. So we're going to look at sorry, let's just say Monte Carlo baseline. That's the better way to put it for our purposes right now. Monte Carlo baseline. We'll do parameter variations separately, but this is Monte Carlo baseline. Okay? It's going to be a Monte Carlo. It's going to run it many, many times. And we're going to say finish. Ready? Get set. Go. There we go. Okay. Ladies and gentlemen. Okay. Alan, I don't know if you were coming in. It's been intense.
No, this will be okay. Everybody's at the right spot, right? You're building, it's all okay. Yeah.
Okay. Okay, ladies and gentlemen.
I got you. All right, I'm not going to help you.
Okay, ladies and gentlemen. So next, what we're going to do is we are going to set the maximum available memory to be a bit larger, like 1024, because we're going to be running several in parallel. Depending on your computers, you may be running 4 of these models at the same time. Don't worry, you're not going to be building 4 at the same time, but running. Okay? Ladies and gentlemen, we are running the main class, and we are going to run it freeform 10 times, just initially. We'll come and leave it open to more. We're going to run it with all the baseline characteristics, okay? We had some baseline, we're going to run it with the population size 1,000, contact rate should be 10, duration of immunity should be 45, and duration of infection should be 10. So 1, 45, 10, but population size should be 1,000. Okay? Okay.
We're doing 10 runs?
10 runs for now. Just to make it manageable for the in the time. Sorry? Free form.
It should be there on top of them.
You created an experiment?
Yeah.
This is a parameter variation experiment.
Yeah, I have the population size, I have everything else except for the 2 buttons on the top.
No, you created, so this is a simulation experiment.
Okay, so this is 1,000. Did you get that? Okay, ladies and gentlemen. Okay, now I'd like you to go and I'd like you to set the stop time to be 1,000. Okay? And I just, you don't have to do this. I just want to run this till time 1,000 just to be sure it looks, I'm not doing anything that's... You notice when you set these experiments, you could set them on a prolonged basis and an unlimited basis, or you could set them to run to a fixed time. And I want to set this to run to time 1,000. Okay, and here it is running to time 1,000. Okay. Okay. Oh, this one died out. Okay, that's interesting. Sorry?
Sorry.
Time 1,000. Sorry?
This is not giving me a run screen.
Not seeing it on the screen.
No, it's not gonna. I'll show you what it's gonna do. You're trying to run it?
Yeah.
Okay, if you run it, this is what you should see.
Nothing.
You should see this. Ready? Get set. You should see a blank screen with this up the top. You see that? You actually need to press this. I mean, we can decorate it with things, but here it's actually running at each of those times. Okay? And it's actually run it 10 times there.
The stop time is not set.
Yeah, but Dina, you want to set the stop time to be 1,000 here?
I think I did.
Did you set the population
Yeah.
size to be 1,000?
I did.
Okay.
Let it get to the end.
It says it's done 10 runs, so I'm trying to see what I see in there.
Okay, yeah, but we're going to go do that exactly right now. Okay, ladies and gentlemen, now what I want you to do, now what I'd like you to do is I would like you to drag into this experiment. So ladies and gentlemen, the relationship between an experiment and main and the model is going to be totally different here. Previously, up till this very point, every time we've run an experiment, it's run the model one time. Remember that? We run it, and we run it with one set of assumptions. Run it with a different set of assumptions. This case, this experiment, we're responsible for running the model many times. It'll run it not just once, but twice, 3 times, 4 times, 5 times. And each time, it'll be responsible for setting up the model, running it, grabbing some information out of the model, using that information, throwing that model away, and then it'll go on to the next run and the next one. It may do that 10 times, it may do it 100 times, okay?
So what are we going to see?
We're going to do it right now. We're going to add in some things to this. Sorry? So, what we're going to do is we're going to add to the experiment, not to main, to the experiment, certain visuals that are going to summarize the runs across many experiments. Okay? So, from the palette, ladies and gentlemen, I would like you to go to the Analysis tab, and I'd like you to drag in another pair. Remember, we've done a lot of these now where we drag in some graph, and we drag in a data set the graph depends on. Remember those? We did it for the scatter plot. We did it for the histogram. We did it for a epi curve. So you're going to drag in a histogram 2D, which is going to be the plot. And then you're going to drag in a histogram 2D data. Okay? So histogram 2D data will be histogram. This will be the incident case count histogram 2D, and this will be over here incident case count histogram. And I would like you to set it to show bins, ladies and gentlemen. Show bins. Okay. 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 What's that?
But that's on the histogram, not on the data.
It's on the histogram.
Did you type your histogram?
I called it incident case count histogram. Okay. Okay. Ladies and gentlemen. Okay. Now, I'd like you to do. I would like you to do a. Here, add histogram data. And what do you think we're going to add as the histogram data associated with this? Anyone? What do you think we'll be adding? Hey? What do you think we'll be adding now? Yeah, exactly. Exactly. Okay? Great. So, ladies and gentlemen, we're going to have here as the title, incident case count. And for the histogram, where it says histogram confusingly, this is incident case count histogram 2D. Okay? Okay, now, ladies and gentlemen, I would like you to go down here and just look, okay, this says update data automatically. I don't think we're going to need that. So I'm going to set it to do not update data automatically. And the rest I think we can leave unchanged, okay? Okay. Okay. Maybe I'll say leave it as update data automatically. I'm sorry. Leave it as that. I'm not sure that we need to undo that. Update data automatically stays on. We don't change anything else beyond this. Okay? Now, we're a lot of the way done, ladies and gentlemen. A lot of the way done. Let's go over to the histogram 2D. So we set this thing to depend on this histogram 2D data set. Next, we'll go over to the histogram 2D. And here, ladies and gentlemen, we're going to set there to be an x-axis range and y-axis range, okay? The x-axis range is going to be from 0 to 1,000 because it's going to be the time. And the number of intervals, ladies and gentlemen, will be 100 intervals. So each is going to be of length 10 days. Okay? 10 days per interval. And we could make it larger, but for now we're going to do that. For the y-axis, the number of intervals is going to be different. We're going to have here between, okay, so that's interesting. It'll be between 0 to, let's say 500. And we're going to say there'll be 100 intervals that way, 100, okay, as well. So this histogram 2D is going to specify, it's for each little unit, each little interval of time, it's going to count the number of times the actual values fall within different value ranges. So if this is going to be a histogram over time. If you slice it at a given point of time, what you'd see is a histogram over values of the number of people who are incident cases for that time. So if you slice this thing vertically at a certain moment in time, you're going to get a histogram. Maybe more cases, more runs had values in this range, and fewer had them above and below. So there'd be a kind of a histogram peaking in the center and then going down. That's the idea here, okay? So there's going to be a histogram, but in 2 dimensions. Okay. So that's the idea. Now, we're most of the way done with doing this. But for this guy here, we want to make sure that, that this is set for this actual 2D data. We make it do not update automatically. We're going to update it. We're not going to ask it to update itself. For that one, I want it to be do not update data automatically. Okay? Are we okay with that? Okay. Are we okay? So again, 100 intervals from 0 to 1,000 for x, 100 intervals from 0 to 500. I'm actually not sure what this value needs to be, 500. You know, I'm tempted, you know, if you let me run this thing for a minute, I could probably tell you how big should it be? Maybe it should only be from 0 to 400 or 200 probably. But let's just run this. And it looks to me most of the time like the incident case counts is less than 100. So let's make it 0 to 200. Okay? I'm sorry for the change, but I think it's quick to do now. So let's make this 2D histogram, the y-axis range, instead of 0 to 500, make it 0 to 200. Are we okay with that? The y-axis will be the number of cases at that time. So x-axis is time, And the y-axis will be the number of incident cases for that time interval. Or in that number of weekly incident cases during that time interval. What's that?
Sorry, something's weird's going on.
Okay. Okay, next. We haven't finished the thought yet. Now we have to go to this. Make sure, again, you're in this parameter variation experiment. Go select it over in Projects window. And I'd like you to scroll down, ladies and gentlemen. Scroll down. And I'd like to go to randomness. And you want this to be random seed. You don't want this every time to run the same thing. So in the baseline Monte Carlo, you want to scroll down to random seed, and you want it to be set it to so it's random every time it's different. Is that okay? That's one thing. Next, in the Java actions, okay, before each experiment run, ladies and gentlemen, I would like to initialize this data set. Just like we did before at the beginning of each month, we threw away all the data in the histogram. We're going to say this dot incident case count histogram 2D. Remember, all these things are in the experiment because the experiment's going to be running main many, many, many times, right? Might run it 10 times, 100 times, 1,000 times, 10,000 times. The experiment will be running main. So this dot incident case count histogram 2D dot reset, ladies and gentlemen. Dot reset. That's what we want. We're going to throw this out, and then, ladies and gentlemen, after each simulation run, we're going to do this. Watch this. This dot incident case count, that same thing, histogram 2D. I'm sorry. Oh my gosh. Oh my gosh. Oh, this should really be called 2D data. This, what's going on?
It is.
Yes.
It is.
Oh man. Okay. So in mine, I made the grim mistake. A database, data set. This should be called, or histogram data, 2D data. This one should be called histogram, and this should refer to, this guy should refer to that guy by that name, 2D data. We'll make sure it's built, but this guy should be called incident case count histogram. This one, incident case count histogram 2D data, and this one should refer to that one, right? Okay. And so I just want to make sure I've named them correctly. This one refers to that one, not vice versa. Remember, the chart refers to the underlying data set. Okay.
Now I'm lost.
Okay, Winchell, Alan? So I just went back to here. I want to make sure the name is correct. This one is the incident case count histogram.
Data, but every time I try to put a name on that chart, it vanishes.
Okay, this is incident case count histogram. That's because it clashes with another name, Winchell, probably.
Well, it may have done because of what we were doing.
This should be incident case count 2D histogram data, this one. Just so we're dealing with the same names. Is that okay? And this one should refer to that one. Right?
Okay,
Right?
there we go.
Are we okay? Do you want me to go on? Okay. Now, in this experiment here, we'll go down and, ladies and gentlemen, this should be this dot incident case count 2D histogram data dot reset, and after the simulation, data dot add, and we want to add to it a whole data set. The data set from where? From the run that just completed, from main. This thing lives in experiment, and it's accumulating the data from each run of main, the data on the number of incident cases for different weeks. And we're going to add it in. We're going to add it in, ladies and gentlemen, to this data set. Now, I just realized this thing we're adding is it's going to be successive weeks. So, but no, it's marked in days, so that's fine. Okay, so add, and this will be root. So that's the name. This is how we call the main that just completed. Root dot, because sometimes models it's called main, sometimes it's called global or whatever. We call it root here. It's just a short name for it. It will tell you that. It says root here, root top level agent, root dot, and this will be incident. It'll be incident. Pardon me for just a second. What is that called? What's our data set called there? It's called, what was that data set? Weekly case count. That's why I can't find it. Weekly case count data set. That's what we want to do. We want to add that in to this. Are we okay with that? Are we okay? So all we're doing is we're taking, we ran one simulation. We take the incident case counts for that simulation from time 0 to 1,000, and we're adding them into this 2D histogram. Okay, so ladies and gentlemen, let's run this thing. Or let's build it. Okay, please build, and TAs are waiting. Winchell and Alan?
So what part do we run, the Monte Carlo?
Let's run the Monte Carlo. Try building it first.
Yeah, this one.
Is it built? Is it built? Okay. Anyone have problems building it? Okay, let's build it. Okay, let's run it. Here's the Monte Carlo. Okay, and now let's run. What are we seeing?
Oh, I have to start it.
You have to do this green button up at the top. Ladies and gentlemen, what is that telling us? Let's run it more than 10 times. Seems it runs it really quickly. Let's run it more than 10 times. Let's run it 100 times, ladies and gentlemen. 100 times. Run this model. You go Monte Carlo, this histogram, you go down to parameters and it says number of runs. I changed it from 10 to 100. I just changed this to 100, ladies and gentlemen, for the parameter variation experiment. We changed this to 100 runs. Ladies and gentlemen, we changed this to 100 runs. It's going to run the model not just 10 times, but ladies and gentlemen, 100 times. And I'm going to start running it now. Ready? Okay, notice accumulating across these runs. For each run it's doing, it's accumulating information about the number of times it's fallen in different bins. Ladies and gentlemen, what does this show us? Indeed. In what sort of variation? Is it unimodal? Where does it seem, what's the single mode? What's the most common single value? 0 for a lot of these. But there's a lot of mass collectively in this area here. Ladies and gentlemen, let's copy and paste this. Right click on this, do copy all. Right click on it, do copy all. And let's go over to Excel. Now, different versions of Excel, in my observation, handle this differently. And I've had terrible luck. Well, some of my students, this is what I get sometimes, which is terrible. But let's try doing it this way. Instead, do the test. Yes, what I did is, I'm sorry, I should explain this. So what I did is I copied all, and then I came to do paste, and it copied it in like this. Now, some of my students in my boot camps get it fine when they do this, and it may be a version of Excel thing. But if you get this, use text import wizard, and you have to do next and tab. Tab is the key. There it is. It's laid out beautifully with tab. And then do finished. Finish. There we go. So, ladies and gentlemen, these are counts of the number of times that, say at time 200, the number of times that the value, the number of realizations, the number of runs of the simulation where the value for the number of infectious cases, Alan, maybe you could get to Vivian, have fallen within this range or this range. And if you go down and look, you start to get quite a few here. About 34 out of the 100 were here. And then, you know, the next level up, you got, the minimum you got was about 40 to 44, 42 to 44. And then you start getting quite a few that are up in this range here, right? Up in this range, sort of the next highest mode is like 86 to 84 to 88. So in short, ladies and gentlemen, there's really a bimodal distribution. There's a lot down here, and then there's a lot which is up here. Now, this is notable because if you were to deal with an average case, you know, Dr. Yan had asked earlier about a mean field model. And here, the average of these, there's almost nothing at the average of these two. There's almost nothing which has this value here. You either have a value well above it or a value below it. It's very bimodal. There's very little at the average of 0 in this, but there's lots above and lots below, okay? So I want to make sure Dr. Yan has a chance to see that. I'm just emphasizing there's that, you know, in terms of mean fields, what we see is a very bimodal distribution. If you copy this into Excel, you will find, you know, quite a lot of probability mass down here at 0, and then you will find quite a lot which lies up here around 100 or so, or just short of 100. And the point is, there's very little in the middle, very little in the middle between this, and so the mean, you know, the mean of these two is not terribly meaningful. If one had a mean field that was in the middle, because there's never any run that's here. It's always either much higher than that or much lower than that. And there's very little that's here. So this is essentially kind of a disease-free state. And this is a endemic state where it's remained present. But you have these a very bimodal distribution. You can see it's quite wide. Now, there is an issue here that we need to deal with. You'll notice that these are alternating awkwardly, 34, 17, 34, 17. It's because we're summarizing things on a 10-day basis, but things that are only being accumulated on a 7-day basis. Okay? So it would actually be better for us if instead of dividing this up so that we sampled every 10 days, we instead sampled every 7 days. So if we go here, by sampling, I mean the bin size. So let's go to this here, this histogram 2D data. And for the histogram 2D data, I would like to go down to this area of the X values. And instead of doing 100 from 0 to 1,000, I'm just going to do 100 from 0 to 700. Each will be exactly 7 days in duration. And I would posit that we'll see less of this kind of regular variation just because we've happened to have sliced it different times during a week or whatever. Some of those would have had 2 weeks in them, 2-week ending in them, and some just 1. And hence, I think it was counting it. So So ladies and gentlemen, up here, this should go 0 to 700 with 100 intervals. Let's run this now. Run. And I'm going to run it 100 times once again. Okay? 100 times. Here we go. Boom. Okay. So it's running, and here we go. And you notice it's running in parallel across multiple boards. That's why those are running in parallel. Winchell, would you be able to get a bit of water? Thanks. Okay.
Can you just explain what the bimodal distribution would mean?
Sure.
Is this infection
Sure.
or-
There's a lot of cases where infection doesn't take off at all, where
It's almost like
it dies out.
It's converging to a diode where it doesn't get, it never gets really going.
Yeah, there's some cases by the stochastics where we infect someone and it doesn't catch. Maybe that person has few contacts, or maybe by chance they don't transmit it to those couple contacts. And if we go look at this data, and I'll go copy it into Excel, this new updated one, here, we'll say don't save. And we go to paste this in. Okay, it's being truculent, but I'll go correct for that. Here we go, boom, and we'll do tab, and we'll do finish. Let's go look at these statistics now. Okay, so if we consider, let's say, time 200 or so, okay, during this week, about 9 out of the 100 cases had a value down here at 0. But then there's quite a few cases here, ladies and gentlemen. You know, there's one that had as few as 34 to 36. Okay, now I've kind of gone off to a different thing. I meant to be at AF. Okay, and then there's, I'd say the highest single value is probably this 110. Which is that single mode, which is 78 to 80. Okay, so there's a few, like about 1/10 of them roughly, that have no takeoff at all. It dies out. That initial person isn't lucky enough to infect anyone, or maybe they infect one person and it dies out then, or something like that. So by the time that time 200 rolls around, there's nobody getting new sick. So it could peter out by chance before this, in the first 1 or 2 or 3 generations often, before it really starts getting going. There's still probabilities I don't infect anyone before I recover. I recover quickly, and before I recover, I don't get anyone. But for most cases, there are people infected, and for those, there's going to be considerable variability. And for most, there's an outbreak, in other words. This is a case without an outbreak. The outbreak dies out prematurely, just peters out. Here, the outbreak occurs. I think he's probably going to go around, but that's really nice of you. Here, the outbreak occurs, and the outbreak is of varying size. You know, basically, if you look at the runs, typically per week, thanks a ton, Winchell, really appreciate that. That's amazing. Between 50 and about 120 people are getting infected here. And you could see it kind of goes down to an equilibrium, or I shouldn't say an equilibrium, it's kind of a quasi-static equilibrium. There's actually, as we've seen, on a particular run, there's some fluctuations, right? This belies the fact that a given run looks a little bit like this. A given run of this might look like this. I'm going to run a single realization. A single realization actually doesn't hop around in a kind of desultory way, and with total randomness, you know, between different things. It actually goes up and down, and where each of these, to be clear, this is like, you know, cycles that are, this is about 100 days, so these cycles are roughly 30 days-ish or so between peaks, and between, well, this peak and that peak. So the point is, we actually have, in a given run, some significant structure here. The parameter variation experiment doesn't really capture that. It's not plotting particular runs. What it's doing is plotting sort of what fraction of the time, or how many runs did the result case counts within certain range. So each of these dots means like there was at least one run where for this time here, the number of people sick in that week was around 120 to 130. Does that make sense? That's what that's showing. And this looks very entropic. It looks like jumping around, but a given run of it will have some variability, of some cycles associated with it that have structure. And sometimes knowing that structure can be helpful for interpreting the data, but also knowing the degree of variability. And what this is suggesting, as Dr. Yan sort of noted earlier, is that different realizations, some of them are high at this point, some of them are low at this point, at this particular point, but they tend to occupy this range. But then there's going to be some small number of black sheep that it never takes off in a serious outbreak at all. Is that helpful? And what I'm saying is there's very few in the middle. This is dead space. Even though it's the average of 2 common cases, there's none here, essentially.
So is that 2 different scenarios for cases within this situation, or is it like the population? Like, is it a scenario that the population will just not get sick at all?
Well, yeah.
Is this that thing?
So to be clear, this is all running it with exactly the same parameters, right? And these are cases where the population just doesn't happen to get sick. And I would venture, if I sat here for a while and I were to run this model 100 times, and probably if I ran it, so I've just changed it to random seed, and probably if I ran this 10 times, there's a pretty decent chance I might get a case where it doesn't take off. I just ran, in fact, it even happened once to me. Okay, this took off, right? Let's try it again. Didn't take off this time. We had a very brief spike of 2 people, and it died off, it looks like, in the 2nd generation or something.
In fact,
Yeah.
the more heterogeneous,
Yeah.
in both senses, either your network structure or the larger the variation of the infectious period, say not exponential distribution, some
Right.
other distribution.
Right.
The more the variation of those things, I say the more heterogeneous it is, the higher the probability it won't take off.
So, and this is a case where it doesn't happen to take off. And so those are accounted for in those small fraction of cases which down there. And from the sound of what Dr. Yan said, and it stands to reason, if we had a highly variable infectious period, for example, some people recover very soon, some people not, you get more of these cases where the first person just happened to recover soon enough they didn't infect people, or they infected one other person who got infected or recovered soon enough that they didn't infect people. So you do have these cases where, there's quite a few cases where you have none, and then there's quite a few where you have a modest number of cases. Is that helpful? Okay.
So like if you're explaining to someone,
Yeah.
say that there was like some probability that nothing would happen.
That's right.
And then, but
The-
more like something would.
That's right. There's some probability. I guess the way to say it is we can't count on a certain future here. It seems likely that there will be an outbreak, but there is a chance that even with our models being sound, that there's no outbreak that occurs and the infection dies out. That's not a sign that we fail to understand, or there's a lack of knowledge here of the bug. It's more a fact that just with the probabilities involved, if you have someone fly into the Ottawa airport with a nasty bug, it is possible that it will cause a significant outbreak, but it is possible just by the luck of the draw that it won't catch. And, when you had SARS, people with SARS going around, I remember flying in through Singapore with SARS, and there were some chance events that occurred there. I knew people who had worked in the labs at NUS, and there was mistakes made in the labs that actually led to an infection. It was a stochastic event. And a model like this can capture these stochastics, and part of the implication of that is you don't always get the same thing. You get different futures that are possible. Now, I want to show you one other thing with this parameter variation. that I should emphasize. This Monte Carlo baseline, if we copy it and we paste it in here, paste. So we have a copy. And I'm going to actually say now Monte Carlo parameter variation experiment. Now we could do things like we could ask freeform, we could ask, well, what if the contact rate is drawn from a distribution or the duration of infection? So just as Dr. Yan had mentioned, we could make the duration of infection, for example, drawn from a distribution. So some people, in this case, we could do it so each individual has variability, which is, I think, the case mentioned. But here we could actually vary the assumptions about the model, uniform across the model, where we have some runs where this is as small as, well, we'll do a truncated normal distribution. So we will do a limit, okay, and it doesn't allow autocomplete here. Okay, we'll draw from a normal distribution. We'll have to truncate it. It could be with a sigma of 2.0 and a mean of 10, and again, that's how any logic has us define it. And it'll be a minimum value of 0. So, well, it'll be the max of 0 and this. We don't want a value that's negative for infection duration. So if this thing is less than 0, we'll use 0. Otherwise, we'll use whatever this is. So I just put this into place like that. And here, ladies and gentlemen, we should be able to build it. And now we're going to run this model with some variability in our assumptions about that parameter value, okay? We're going to run this model that we're assuming different things in different runs about that parameter value. Some of the runs assuming a value that's higher, some of the runs assuming a value that's lower. Now we get variability that's not merely stochastics, it's also for different assumptions about this duration of infection. We get results, okay? And this would change those results. Let me show you another. So this is what's called a Monte Carlo analysis with drawing the value of duration of infection from a distribution, as might be suggested empirically from the evidence. We're not sure what the true value is, and we'll examine a distribution of possibilities. May I show you another case? Okay. I'd like you to copy this, and I'd like you to paste it in. Paste. And now, for this new one, for this, I'd like to call it Monte Carlo parameter variation grid-based. We will have this varied in range. We will systematically vary the ranges of these parameter values over a range. So we will have duration of infection go from a value of 5 to a value of 15 with a step of 1. And we will have the duration of immunity go from a minimum of 30 to a maximum of 75. This needs to be a range, value of 30 to a maximum, ladies and gentlemen, of 75 with a value of 10. 15. Okay, Winchell, or?
Range, okay.
You have to set it to range, yeah. So now, you notice we don't specify the number of runs. The number of runs are implied by this. I have a certain number of values that I'm exploring here, a certain number here, and it multiplies them. Here I'm doing a grid search. I'm doing it for all possible values. Now, I can run this, and I will run it here. Do you want me to show that there?
I've got it. Just do it.
Sure.
Is there a way,
Uh-huh.
with
Winchell?
press something?
Do you, so you may have to set this to range here.
Yeah, I did that very in range, and then how come I kept pressing this column?
Up at the top, you may have to select.
It's varied in range. Is it varied in range at the top?
How come I need to get to this column?
Winchell, is it set to varied in range at the top?
Right, it is, but I believe it's probably one of the versions you've mentioned that they have some like mislabeling, the variety in range and the free form. You remember one of
Oh yeah.
previous version?
Yeah, there was that bug with.
This will be awkward.
Well, Winchell, you just switch it back, I think, to this or
Yeah,
something,
I was-
or you close it and you reopen the experiment.
Yeah, that's probably it.
So this should be varied in range. Yeah, there's one bug in AnyLogic 7.2 or something where it mislabeled these.
Oh.
Okay.
I think that's really the issue.
What's the issue?
This is the range.
Okay, so now we should be able to run that,
Okay.
and it will run it. What was it mislabeled?
Nope, there are two range to be specific.
Yeah, 2 range. Yeah.
You specified-
So ladies and gentlemen, now it's running it for different values of those experiments in a systematic way. And you'll notice here that it ran 44. Why? Because it's 11 different values of this plus 4 different values of this. And here, okay, now that's kind of an interesting result. It's got duration of infection, duration of immunity, and most of the times it died out early on here. There's probably some, yeah, I could see there's some here that are higher here, but it's not many. Maybe we'll up this upper one to be another up to 105 duration of immunity. Well, okay, wait a minute. That's not going to be. Yeah, that's duration of immunity is not going to help it from dying out. We'll get up to 20 duration of infection. So here we are systematically examining combinations of values for these, and it is running the model right now. Mark my words, it is running it a single time here for each of these possible combinations.
Whoa, that says something very different.
What's that?
What are the axes in this again?
This is again time, and this is value, number of people who are incident cases at that time.
Well, is that income on the bottom?
No, this is time.
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 And,
Okay.
and the number of cases by day or
By weekly case
something,
count.
Number of cases per week.
Yeah, weekly case count. So,
Okay.
ladies and gentlemen, one thing we didn't address is that for each of those runs, there'd be some variability. There's stochastic variables. So what you could go down is do use replications here. And use replications allow you to tell it for each of those runs in the grid, how many times to run it. For each of the for each parameter vector, for each assumption of those parameters, how many times do we run it? Because of stochastics. And here we can run it 10 times. Where did I get that? I went down, ladies and gentlemen, to this replications area, and I selected use replications. Do you see that? Okay. Ladies and gentlemen, and we want to be 10 replications, okay? And we want to run this thing. And now it's going to run slower because it's got to run for each possible combination. It's got to run got to run 10 for that combination. But it allows us to be more confident about the sort of values involved. Okay? Okay, so that's all we have time for to look at that. I want to show one other thing for this model, if I could. Is that okay? Okay, and that will be how we can output data to a file from this model. Okay? And what I'm going to do here is because we're running it in a parameter variation experiment, I don't want to do this output every single, well, I could do it every single run. It will just be outputting again and again and again and again. Okay, so ladies and gentlemen, what I'd like to do is I'd like to go back to main, okay? Like to go back and we're going to add to main. So I should really be saying that. Do you want to upload this? Would that be useful?